Episode of Mr. Avila Physics. Today, we're going to be discussing Coulomb's law. In previous video, we learned that charges exert a force on each other, right? We learned that opposite charges attract and same charges repel each other. But what does this force or what factors affect the magnitude of this force? Now, one factor is for sure the magnitude of the charges. The greater the two charges, the greater the force of repulsion or attraction between them. And a second factor is the distance between these charges. Okay? So the larger the charges, the stronger the force between them. The closer together the charges are, the stronger the force between them. Back in the day, Coulomb discovered that the relation between the force and charge was directly proportional, but the relation between the force and distance was inversely proportional to the square of the distance between the charges. So in equation form, we can write Coulomb's law as F equals K charge 1 times charge 2 over the distance squared. Keep in mind that the distance is the distance between the center of the charged object to the center of the other charged object. If the object is a particle, then there's no need to worry about it. But if the object is a charged sphere, then we have to look at the center of that sphere, not just the edge. Okay? So be very careful and very attentive about that. The value of K is 9 times 10 to the power of 9 newtons meters squared per coulomb squared. Now another way of representing K is by saying that K is also equal to 1 over 4 pi, let's see if I can do this, 1 over 4 pi epsilon 0, where epsilon 0 is known as the permittivity of space. Now, most of the time, our examples and everything is going to be involved in the air, right? Okay, we're going to be looking at charges that are in the air. But if we were going to look at the behavior of charges inside quartz or inside underwater or anything like that, then we would have to change the permeability of space, okay, to a different value. But this is more just for extra knowledge. It's another way of representing K. Okay. So since force is a vector quantity, force will have a magnitude and a direction. We already looked at how to find the magnitude. Now let's look at the direction. Now, the direction of the electric force will always be along the line joining the two charges. If the force is positive, then the direction of the force is directed away from each other. Because if the force is positive, then that means that both charges have the same sign, which means that it's going to be a repulsion force. But if the force is negative, then the force is directed towards each other because the charges have opposite signs and opposite charges attract. So if both Q1 and Q2 are positive, then when we multiply Q1 times Q2, we're going to get a positive value of F. If both charges are negative, same thing. So there's a repulsion force. But if the charges have opposite signs, then there's a force of attraction. All right. So when we first talked about charge in a previous video, we said that charge was the excess of electrons or the excess of protons. But we can't really quantify charge by that. We need a unit. okay? And the SI unit for charge is the coulomb. Now, being as the electron or the proton is the smallest possible charge possible, right, so far, then this will be known as the elementary charge. And the elementary charge has a value of 1.6 times 10 to the negative 19 coulombs. Now, be very careful with this value. This value is defined as a positive number, right? So that means that the electron is going to have a charge of negative 1.6 times 10 to the negative 19 coulomb, while the proton is going to have a charge of positive 1.6 times 10 to the negative 19 coulombs. Okay, so be very careful when looking at this. All right, let's look at some examples. So here we have three charged particles that are arranged in a line as shown. Calculate the net force on particle 3. That's the particle the farthest to the right due to the other two charges. Pause the video here, take a couple of minutes and see if you can solve this problem. All right, welcome back. Okay. Hopefully you were able to solve this problem and we'll be able to check your answers shortly. Okay, now, when looking at this problem, we have to look at several things. We have two charges affecting this third charge. And we have to look at the signs of these charges. The force between Q2 and Q3 is going to be a force of attraction, right? Because the charges are opposite signs. But the force between Q1 and Q3 is going to be a force of repulsion because the charges have the same sign, right? So when you do your calculations, be very careful about that. Now, in this example, all three charges are particles, which means that the distance is already measured between them. But if instead of, let's say that if instead of particles they were spheres, three large spheres, then it'd be the same thing. We would measure the distance from center to center to center, not from the surface of the sphere, but from the center. So just be very, very careful, very careful about that. Okay? All right, back to this example here. So in this example here, we have this. So now we have to calculate the magnitude of this force, the magnitude of this other force, and add them together. And as we can see here, there we go, right? These are the magnitudes of the two forces, 1.2 and 2.7. And as we said, one of them is a force of attraction because of the, because of the negative sign. One of them is a force of repulsion because of the positive sign. We add them together and we end up with a net force of 1.5 newtons to the left. All right, let's look at another example. In this one, we're going to calculate the net force on charge Q3 due to charges Q1 and Q2. This one's a little bit trickier because it's not in a straight line as the previous one. So take a few minutes, think about this example, and pause the video while you work it. All right, welcome back. Hopefully you have an answer for this example now. All right, so let's look at this problem right here. Here we have a triangular arrangement of charges. And we're looking to find the net force on charge Q3 over here. So Q2 and Q3 have the same sign charge, right? So this is going to be a force of repulsion and it's going to point in this direction, right, upwards. Q1 and Q3 have opposite signs, so this is going to be a charge of attraction and it's going to point in this direction along the dotted line. It's hard to draw on the track path. Okay. Now, now we have to calculate the magnitude of this force and the magnitude of this force and add them together. But as we can see, the angles are different, right? So now we're going to have to work with components. This force we're going to have to break into a horizontal component and a vertical component, and then work with vectors like we're used to, right? We know this angle here is 30, right? So now we can find this complete horizontal component, the vertical component, and go from there. All right, let's take a look at how your textbook solved this example. Here we go. We have the magnitude of both forces, but then one of them we have to break it down into components, right? And then we add the horizontal component, we add the vertical component, and we use Pythagorean theorem to know the magnitude of the force and the angle of the force. So our net force would be 290 newtons at an angle of 65 degrees. Let's see if the angle makes sense. We have this one, and then this vertical component will be greater than that. So it makes sense that our net force would point somewhere in this direction right here. All right, so this would be our net force right there. All right, hopefully this examples made sense and you're able to remember what we talked about from Coulomb's law. All right, thank you all for watching. See you next time.